All right, a point of inflection occurs where a graph changes concavity. Okay? So if the graph changes concavity, that's called a point of inflection. So if you go all the way back to those points that I put on the very first graph on the first page, those were my points of inflection. I just wanted to identify those. So where f changes concavity, then you have points of inflection. So this part right here is really what you need to think about. So find the points of inflection for f of x in number 2. So how many points of inflection do I have in number 2? 2. I have one at x equal negative 1 and one at x equal positive 1 because that is where the graph is changing concavity. Technically, we would want to put negative 1 comma something and 1 comma something and plug those two x values back up into your original f of x to find the actual point of inflection. And we need to justify by saying because f double prime of x changes signs. Yeah, it doesn't matter whether, like for a maximum, f prime needs to be changing from positive to negative. But for a point of inflection, your concavity just needs to be changing. So it's not, you don't need to specify whether the second derivative is changing positive to negative or negative to positive. A point of inflection is only going to occur where the second derivative equals 0 or where the second derivative is undefined, because that's the only time that your graph will change concavity. Now, but that doesn't necessarily mean that if f double prime of c is 0 or f double prime of c is undefined that you automatically have a point of inflection. What would be a situation where you've got the second derivative equaling 0 but you don't have a point of inflection? What would show up on your sign chart? Yeah, like a double negative or a double positive. So if I go back to this sign chart right here, and when you put these zeros of your second derivative down here on the bottom, if you had gotten if we'd gotten plus plus negative, then we would not have had a point of inflection at x equal negative 1, because at x equal negative 1 your derivative is not changing signs. So at a point of inflection, the second derivative will be 0 or undefined, but you won't necessarily have a point of inflection at every point where the second derivative is 0 or undefined. All right, I am going to skip over number 4. Literally, this is a much easier problem because it's a polynomial. You take the second derivative, you find your zeros, you make your sign chart, determine your concave up, concave down, and your points of inflection. We have time, we'll go back to that. Okay, there's also something called the second derivative test. I know, because I was being lazy and I'm running out of time. So you go back to the original and plug in at 1 and negative 1. Okay. All right, if f is a function and f prime of c equals 0, so the first derivative equals 0, and the second derivative exists, if f double prime of c is greater than 0, then f of c is either going to be a relative min or a relative max. So let's think about this. F prime of c equaling 0. That means you have a horizontal tangent line, right? Okay? And if you have a horizontal tangent line, and if your second derivative is greater than 0, is that concave up or concave down? That's concave up. So if you have a graph that's concave up with a horizontal tangent line, that point is a relative min. And if you have a part of the graph that is concave down, because the second derivative is negative, and a horizontal tangent line, that was a bad horizontal tangent line, then you have a relative maximum. The key here is that f prime of c equals 0, which means you have a horizontal tangent. No. So you find your critical numbers, and you find where you have horizontal tangent lines. Then you figure out whether the second derivative is positive or negative at that point, and if you're concave up with a horizontal tangent line, that's going to have to be a minimum, and if you're concave down with a horizontal tangent line, that's going to have to be a maximum. Yes.
Number 5. For f of x equals negative 3x to the fifth plus 5x cubed, use the second derivative test to determine whether x equal 1 is a relative maximum, a relative minimum, or neither. All right, so in order to even think about using the second derivative test, we have to first determine whether x equal 1 is a critical point. And to determine if x equal 1 is a critical point, we need to take the derivative of f. So f prime of x equals negative 15x to the fourth plus 15x squared. And if x equals if x equals 1 is a critical point, then f prime of 1 will either equal 0 or be undefined. So f prime of 1 is going to equal negative 15 plus 15, which does equal 0. So x equals 1 is a critical point. And you can only use the second derivative test if your x value is a critical point. So then the next thing that we would do is to determine whether the second derivative is positive or negative at x equal 1, and that will determine whether we have a minimum or a maximum. So the second derivative is going to equal negative 60 x to the third plus 30x. And then we'll plug in a 1 into our second derivative. So f double prime of 1 equals negative 60 plus 30, which is negative 30. And that is less than 0. So you can either look back up at your, right up above on your notes, and see that if the second derivative is less than 0, when x is a critical point, then you have a relative maximum. Or I have trouble memorizing that. So what this is telling me that the second derivative is negative, that's telling me that the graph is concave down at that point. So I have at x equal 1, the graph is concave down, and the slope or the first derivative is 0. So therefore I have a horizontal tangent line, and therefore x equals 1 is a maximum, is a relative max. So x equal 1 is a relative max because your justification would be that f prime of 1 equals 0 and f double prime of 1 is less than 0. And as you're working this out, I would expect you to label all of these things the way that I have. When you take the derivative, write f prime of x. When you plug a 1 into the first derivative, you need to label that as f prime of 1. When you take the second derivative, label it as f double prime of x. When you plug 1 into the second derivative, label it as f double prime of 1. All right, number 6. F of 1 equals 3, f prime of 1 equals 0, and f double prime of 1 equals negative 5. What can you conclude about the point 1, 3? All right, well, the first thing that jumps out at me is that f prime of 1 equals 0. So that means that x equal 1 is a critical point. So 1, 3 is a critical point because f prime of 1 equals 0. Now, if x equal 1 is a critical point and the second derivative is negative, then by the second derivative test, I know that 1, 3 is a relative maximum. And the reason I know that is because f prime of 1 equals 0 and f double prime of 1 is less than 0. All right, this last problem. This was an actual problem from an AP exam. Consider the differential equation. All right, we haven't had that vocabulary word yet, but a differential equation is just an equation that is a derivative. So the fact that they're giving me dy dx equals 2x minus y, that means that it's a differential equation. It's an equation that represents the derivative of some function. So does the graph of y equal f of x, so does the graph whose derivative is 2x minus y that passes through the point 1, 2 have a critical point at 1, 2? If so, is 1, 2 a relative max, a min, or neither? Justify your answer. All right, so the first part, that's easy. Critical points are where the first derivative equals 0. So in order to determine whether 1, 2 is a critical point, I need to determine whether the first derivative is 0 at that point. All right, the notation for this is what we are doing is that we're taking the point 1, 2 and plugging it into dy dx. So the way that you write that is you write dy dx and then you put a little vertical bar right here and then your point 1, 2. And what that notation means is the derivative at x equal 1, 2 equals, and then when I plug in a 1 for x and a 2 for y, I do get 0. So since dy dx, or the first derivative, equals 0, then yes, 1, 2 is a critical point. Okay, so since 1, 2 is a critical point, then I have the opportunity for this to be a minimum or a maximum. It doesn't have to be a min or a max, but I definitely have that possibility there. Now, previously in the last section, the way that we would determine if a point was a minimum or a maximum is we would make a number line with f prime and determine whether at x equals 1, my first derivative was changing from positive to negative or negative to positive. Well, that's impossible to do here because if I want to do a test point to the left of x equal negative 1, then that would be at x equals 0 or anything less than x equal 1, but the logical one would be to put 0. So, but if I plug in a 0 for x, I don't know what the corresponding y value is right here, and I'm not given a formula for f of x to find that corresponding y value. So therefore, we cannot use the first derivative test to determine whether or not this is a min or a max. So we're forced to take the second derivative and use the second derivative test. So I need to take the derivative of dy dx. So that would be d squared y over dx squared. And the derivative of 2x minus y would be 2 minus dy dx. But remember that we never leave the second derivative in terms of dy dx. We always replace it with what dy dx is in terms of x and y. So d squared y over dx squared would equal 2 minus, and then dy dx is 2x minus y. And if you want to simplify that, that's fine. It would be 2 minus 2x plus y. So my second derivative equals 2 minus 2x plus y. And then all I need to do is determine whether that second derivative is positive or negative at the point 1, 2. So remember your notation would be d squared y over dx squared. Put your little bar, and then the point 1, 2. And that tells me that I'm plugging in the point 1, 2 into my second derivative. So when I plug in a 1 for x and a 2 for y, I get 2 minus 2 plus 2, which equals 2. So, because my second derivative is greater than 0, and my first derivative equals 0, the point 1, 2 is a relative minimum. So 1, 2 is a relative minimum because dy dx equals 0 and d squared y over dx squared, or the second derivative, is greater than 0.